Hey everyone, welcome to Decision Analysis and Forecasting for Agricultural Development. I'm Cory Whitney. Today we'll be talking about model building. Essentially, how to get from that causal impact pathway, that theory of change, or causal diagram that you've created, how to get from that to an actual programmed model that you can use for developing forecasts. I'm really excited to deliver this content. It's going to be challenging this week, but I'm sure we'll make it through together, and you'll let me know if you have any issues. So just a quick recap in this portion of our talk on concepts and motivation. You recall the meaning of sustainability and this simplified version of it in this Venn diagram. It represents the balance of these three pillars of sustainability, that is the social, the ecological, and the economic aspects of any system. And the question for us and the motivation for these modeling procedures is really a question of theory, research theory. Is our job as researchers in agricultural development to take a small piece of one aspect of or one small aspect of a system and go dive deep and to look deeply into that aspect, to do deep research on that? It can certainly be useful in many instances. Basic research is important. It's critical, as we've seen now in the pandemic times, of course, that basic research, the results of basic research are being brought up and implemented into solving some of these big issues. So it can be useful, but if we're trying to address system level and interventions at that level, then we may need another approach. And so the question is, should we try and take a holistic perspective? Should we try to take a broad view? And if we do it in this way, we can provide as much information as is necessary. We mock up the important parts of the whole system and use this to guide decision making. So instead of doing a detailed study in a small piece, we do a less detailed study, but we try to capture all the important aspects that belong in our assessment. If it's our ambition to predict the whole system, we may also want to consider decision relevant thresholds. These are not always clear. As we gather more information, our decision recommendation may change. That is to say, as the research effort, the number of disciplines and funding goes up, then we may make a different decision recommendation. So early on, we may study a single aspect. We may study very deeply one little piece. We do some more studies and these add up. We begin to get a better, more holistic and more systematic understanding of how the thing functions, how our intervention might work. And in the end, we try to put all these pieces together. We may not have a very clear picture, but this is the idea behind a typical research project. You invest lots of money and you get all of the little research teams, all of the smaller projects within the research to fit together. So our ability to predict system outcomes should increase as we increase our total knowledge in this sort of traditional approach to doing a research project. But what might happen is that our decision recommendation, that is what it is that we think is reasonable for an intervention, may change. So let's say here in the early stage of the research, we just measured yield of a particular plant. And based on the intervention, the yield of the particular plant would increase, and therefore we might recommend that it should be done. But later on, as we begin to understand social and ecological implications, maybe gender dynamics, maybe there's some other sustainability-related outcomes that are relevant to our decision-making, perhaps those yields would not, perhaps there's something in the market chain or some other dynamic where those yields would not actually lead to the real intended outcomes, that is betterment of society or otherwise ecology, etc. So as we gather more information, the decision recommendation may change. And if we're honest about uncertainty and say what we can really say based on what we've looked at, then we give actually very large confidence intervals for incomplete studies. We have high skepticism here about what we're sharing and any decisions that we're trying to support, any recommendations that we make. And the error only becomes short. That is, we report with less error, still uncertainty certainly, but less. When we have very comprehensive assessments, we can say things with more certainty. In this way, we avoid, if we can communicate in this way, we can avoid valuing at zero those elements that we haven't included in our assessment. This works really well for systems that are too complex to fully understand with available resources, and for supporting decisions that must be made without perfect information. So our question is really, what's the best option according to our limited understanding? So we build, as we've been talking throughout this course, we build these causal models, balanced models of complex systems. We recognize what we already know, that is to say, all of the imperfect, random information, multiple perspectives, and uncertainty. We use empirical, expert, and local knowledge to gather available information, to make forecasts, and to identify knowledge gaps. And we can make forecasts of system outcomes without perfect information by describing this uncertainty that resolves. So let's go back a little bit. Let's say this is the system we wish to assess. Let's say this is a farm system. You'll recall this idea that understanding the system by studying a small part is dubious. That is to say, we could take one piece and try to study that. But it may be the chance, maybe the case that we do a lot of these studies and they don't actually fit together, right? Here's our study on yield, and that has a number of different factors and outcomes, right? And then we have a study on gender, and we have a study on other things, and maybe these, we can't really figure out how to fit them together. So zooming in on these details is one way to look at it, or another way to look at it is to think more abstractly, to think about a system in its holism, right? To think about how these, before we try to do a detailed study on a little piece, to think about the whole system. What this might look like when we try to zoom in, it may look like just a bunch of dots, right? This is a divisionism, part of a painting of a post-impressionist artist, Soho. And so we can't really see great detail, as much detail as we would here on the yield dynamics, for example. But when we zoom out, right, then we can see that this is a church on the riverbank. That this we get a more holistic perspective. We can see the whole system, and we have enough detail here to provide some information about what we think the intervention might mean in terms of bigger system dynamics. We do this coarser assessment of all the essential parts. So going a bit deeper with this same analogy, what if instead of gathering all of the measured data on easy to reach things, that might be us here walking along the path, we can measure all these things that are close, and we'll measure them in great detail. But what if instead of that, we try to think about what we already know, to quantify our uncertainty about all the things that are considered important. So here we've sort of captured, with this orange arrow, sort of captured the whole landscape. And I'm saying, okay, let's try to gather all of the things that the uncertainty that we have about all the things we know. And we describe our uncertainty about the functioning of the whole system, even those hard to measure factors. So we describe the uncertainty in our case, and what I'll be talking about today, in the form of uncertainty distributions. There are other ways to assess this uncertainty, but all the hard things to measure are captured in this method. So we take that assessment of uncertainty, and technically what this looks like is that we create a impact pathway for a decision. And we use that impact pathway as a Bayesian model. Our distributions of uncertainty are randomly sampled, and we run the model many, many times, thousands of times with random draws to produce some kind of comparison of, let's say, baseline versus intervention, or different types of interventions versus the baseline. We can provide these distributions of uncertainty, much like weather forecasters make suggestions about storm paths. So these distributions of uncertainty are randomly sampled, and we run the model, usually 10,000 times if we're running a Monte Carlo with random draws. It allows us to work with variables that we don't have perfect knowledge on. Requires, though for us to characterize our uncertainty about them. Common methods are that Monte Carlo I spoke about, also Bayesian networks. We use these distributions as the inputs, because where precise values are unknown, and we create these distributions as outputs, and we look at the differences and when we're making decision recommendations. So essentially that impact pathway model is representing this pathway from the change that we'd like to make, the intervention that is proposed, the thing that the decision maker is considering, and the outcome that they would like to, or that we would like to see in the world. That is to say, better outcomes for rural farmers, better outcomes at the farm, maybe just at the economic level, maybe for society, maybe for the world, based on a change that we're proposing. This is known as a directed acyclic graph, DAG. And a directed acyclic graph just means that, first of all, it doesn't have any cycles. So the arrows here are not in a circle, right? They don't go from this and back to this again. And the nodes, that is, these variables, these circles represent variables, also called nodes. And there are these arrows which represent the relationships. Each of these arrows goes from one node to another, right? From change, for example, to this variable. And it's just representing in the end a logical impact pathway with no closed loop. So again, there's no, we don't see change influencing this variable, which influences this variable, which then influences change again. We have to describe these interactions logically so that they move in a logical order. So what can we do with that DAG? Well, we had a nutrition question about the future of home gardens and agricultural policies in Uganda. Those policies in Uganda favor large-scale staple crop production over traditional home gardens. And we wanted to know what's the human nutrition implication, and should farm scales grow? So actually, we built this comprehensive model, programmed it with existing data to forecast policy implications. Home gardens, these things are just smallholder farms, basically around homes, and they're very complex and heterogeneous. So coherent evidence on their performance was difficult to produce, but we had some data. And we programmed these models with existing data, and we found a likely influence on the preference for and access to quality nutritious foods, and likely negative outcomes for rural households and rural livelihoods, but no appreciable influence on hunger, but likely increase in the prevalence of micronutrient deficiency. This is, by the way, a high-level sketch. I may have shared this with you before, but you can check out the papers if you want to see this in greater detail, and also look at the code for how it's been programmed. But the highlight here is really just that what we're able to do, since we don't have data on everything, we can represent these things with uncertainty, and we can provide some kind of information to decision makers related to trade-offs, which have to be negotiated. So we can make those trade-offs explicit and support evidence-based agricultural development interventions, in this case in Uganda. An additional benefit is that we can mine those model results for stochastic information about different variables. In this case, the model showed differential effects on total production area. So that's under the policy that they wanted to implement to get rid of smallholder farms and move to large scale farming systems. You can see down here the non-food production area. That is the area that's not used that's used rather for producing things which are not intended for food. That home gardens have much less of that. So most of the area that they're using is for food production, but in the policy, they're growing things for export, a lot of things for export like coffee and tea. And in the total production area, that is the total area that's available, it's greater in those policy farms as well, somewhat. There's rather a lot of uncertainty here, but it's somewhat greater in the policy farms, because as you can see, this is a sketch of a typical home garden, and they of course need room for their home, and they have somehow places to hang out. They have a toilet and a kitchen, so they need space for themselves, for pathways and roads. And of course, if this is just planted with staple crops or coffee, then that there's no need for these spaces to be occupied by people. We can also look at the nutrient content of the various crop types. So we can mine that model to find these distributions of uncertainty related to those as well. So these are, of course, based on our inputs that we've provided from nutritionists, from others, and from the literature. And we can see here, for example, that from these 10,000 model runs, we can see the distribution of nutrient contents. For example, fruits had a very high vitamin A compared to others. And of course, staples had a very high energy content compared to other food types. Spices had high energy content, but of course you won't be eating those. Nobody's eating those in major quantities. So that's less interesting than, for example, pulses and staples for energy consumption. So effectively what we do is take existing data sets, use expert knowledge, all of the existing sources of information. We feed these to a carefully peer-reviewed formulated conceptual model. That's what we've been talking about, those DAGs, those directed acyclic graphs, those theories of change or impact pathways. We feed these distributions of uncertainty based on what information is available. And here's an example of how that works. It just, the Monte Carlo algorithm basically selects randomly from our distribution. And if it's something like this, like a rather normal distribution, it'll select quite a bit more from the middle of that distribution and less out at the tails, according to the shape of the distribution. And here, for example, are those model runs that favor the agricultural policy in Uganda, right? So some of them favored the policy. In some cases, we said, oh, policy is better in terms of whatever, in terms of the outcome of interest. That's in red here. And then others favored the Uganda home gardens, rather, not the Uganda policy, but the home gardens. And in this case, the variable of interest of outcome was, for example, nutrition outcome was better in the case of the home gardens, in the case of keeping the home gardens. So home gardens in this particular case with this particular outcome would be a better choice. We would make a recommendation to keep the home gardens in place. So we provide these forecasts based on all the costs, benefits, and risks. It's the result, as we saw, of many draws of the model. And it shows our uncertainty based on the best estimates, best calibrated estimates. So you will now be, in the rest of this semester, you'll be responsible for building your model. And you'll be integrating these ideas and trying to take the big picture, trying to get inspiration from these methods. And basically you're going to build a model, build a decision model, and include that uncertainty in that model. You're going to work with decision makers, define outcomes, desired outcomes. So you have to figure out what those are, what kind of sustainability issues are of interest, and define the different options that are available, the interventions that have been proposed, and identify those expected impacts and influences, and hopefully, and I don't think this is a high bar, but hopefully actually support some decision making that needs to be made. And yeah, enjoy.